now we can able to see how the ideal curve is changing in the practical cases, non-ideal IVFX. So in this topic, we will be discussing. So in practical cases, due to what are all the things your output current is decreasing or increasing. So if you see, the black line is the ideal curve, the blue line is the corresponding practical curve for the same input conditions. If you see these two curves, you compare. So due to many reasons, uh, it is decreasing from the ideal response. So we are going to discuss about what are all the non-ideal thing which affect the output current flow for the same input condition. First one is mobility degradation and velocity saturation. So as we see, so I will explain with the structure. Yeah. This mobility degradation and velocity saturation is happening due to lateral electric field and vertical electric field. So lateral electric field is applied between source and drain, that is your VDS. So lateral electric field is VDS by L, and vertical electric field is VGC divided by T naught. So due to lateral electric field, what is happening is as lateral electric field increases, so you will be having higher potential difference between source and drain. So you will be having more driving force. So it may affect the flow of electron from source to drain. So many electrons may uh, escape. It may try to escape from the channel, and it will spread across the body, the p-type body. So due to which we will lose more electrons through this channel. So conductivity will be less. So second case is due to vertical electric field. So vertical electric field, while applying more potential by this way, electrons are moving in this direction. We are applying from the force from the top. So what will happen is, so it will again disturb the flow of electron from source to drain. Again, your electrons moving in the channel will get escaped and it will spread across the body. So this is the two cases of mobility saturation and velocity saturation and mobility degradation. So due to velocity saturation, as the number of electrons get reduced inside the channel, so due to lateral electric field, the speed and the mobility speed get affected. That's why the thing velocity saturation, a constant velocity will be uh, gained by your electrons. So we can't able to further improve the speed. As speed decreases, your current flow also decreases as the number of electrons are less inside the channel. Then this may not, you might have, if you see in your hard copy of the textbook, this title were not there. So we will be directly starting with body effect only, that third edition. Actually, in the fourth edition is your actual textbook. So in your last regular paper, they have specified a question that, so what are all the thing which will affect the threshold voltage in non-ideal case. So you have to specify these three things: body effect, drain induced barrier lowering, and the short channel effect. These three things are expected. In the third edition textbook, this topic is missing. Actually, they have specified, they didn't combine these concepts. They are specified separately. So I will explain what is body effect. This is a very, very important topic. In one question paper, they have asked it for 6 mark also. So in body effect, so if you consider a single nMOS transistor, we are not minding about the fourth terminal substrate. So the VSB, the source to body potential, we will be considering as 0, approximately equal to 0 when we are treating a single transistor. Actually, VSB value is not 0, it is a small amount. We will be considering, we are neglecting that value actually. It's approximately equal to 0 in, while considering a single transistor. But we are combining or cascading several nMOSes in series. This VSB value comes into action. It will accumulate and it will affect the threshold voltage. So as per this equation, as VSB increases, threshold voltage increases. VSB decreases as threshold voltage decreases. So it depends on how many number of transistors we are going to cascade. If the cascading is very, very high, so it will result in increasing threshold voltage. If threshold voltage get increase, what will happen? So threshold voltage is the actually barrier potential. So in order to overcome the barrier potential, we have to increase the input voltage again. But actual aim of our design is reduce the area, reduce the power, and increase the speed. The second point is reduce the power. If you want to reduce the power dissipation, we have to reduce the input voltage. Actually, power equal to VI, right? So we can't able to concentrate on current there. So by decreasing the input voltage only, we can able to reduce the power dissipation. But in this case, as VSB increases, threshold voltage increases, so barrier potential increases. So it is making us to provide more input voltage to overcome the threshold voltage. That is the very, very main effect, body effect in non-ideal cases. So it will negatively impact the design. Also, you have to specify all these equations also. Second thing is drain induced barrier lowering. So barrier lowering, actually drain induced barrier lowering is a positive impact for the design. Due to drain and body potential, drain and source potential, as it is increases, threshold voltage decreases. That is the concept of drain induced barrier lowering. So as threshold voltage decreases, we need to apply only small amount of voltage to make the inversion happen. So that is a positive impact. Body effect is a negative impact for the circuit. And short channel effect also come as a positive impact, as we have seen in the saturation region, how that pinch off is happening. That concept only they have specified. If the channel is very, very less, so that will also affect in low threshold voltage. In some cases, it may affect in reverse short channel effect also. So that will affect your transistor negatively. So leakage. So leakage current will flow in the opposite direction than your IDS. So in nMOS, IDS current is flowing from drain to source, but this leakage current is flowing in the opposite direction, that is from source to drain. So this is happening mainly when your transistor is in off condition. So when this leakage current is flowing, so it will actually we are not activated the transistor at that time. So when this transistor is flowing, this may imbalance the junctions. So it will negatively affect the junctions. Here junctions means here you have an PN junction because your substrate is P-type, right? So you will be having a PN junction here, you will be having a PN junction here. So this will be affect your junction imbalance. So that will be negatively affect your circuit. So due to leakage, your circuit may get damaged. So subthreshold leakage also the same case, subthreshold leakage, but here if you consider leakage and subthreshold leakage, here your transistor is completely off condition. Here your transistor is not off. Your transistor is on, but you are activating in below the threshold voltage level. That is the case. Here also you will be having the leakage current that is known as subthreshold conduction. Here also the current will be flowing in the opposite direction that of your. This is happening mainly due to the majority charge carriers. In my actually in nMOS, due to minority charge carrier only that due to electron only channel inversion is happening, but here due to holes concentration in subthreshold region, the opposite current will flow that will be reduce the net current. That is the concept of subthreshold leakage. Gate leakage. So gate leakage is the leakage which is happening near the gate terminal. Actually, this concept you might have seen as tunneling effect in the third edition. So if your gate oxide layer is very thin, so whatever input voltage you are applying to the gate will be sufficient for making the electron to penetrate from gate to body. So that is known as gate leakage or tunneling effect. So that can be overcome at the time of design. So you need to have a trade-off between this leakage as well as the silicon dioxide layer thickness. So if you increase the silicon dioxide layer thickness, that will result in increase in threshold voltage. So again, input voltage has to be high. Then only it can able to your gate can attract more minority that electrons from body to silicon dioxide layer. But silicon dioxide layer thickness is high means you have to apply more input voltage to make to the inversion happen. So you need to have a trade-off between this tunneling as well as silicon dioxide layer thickness at the time of manufacture. Junction leakage. As we have specified, this is a Cmos circuit. In the single wafer, we have formed an nMOS and PMOS. This thing we have done in our laboratory also. So in order to make a CMOS inverter, we have to, initially we have a P substrate, so we can able to form an nMOS directly, but we can't able to form a PMOS above the P substrate. So we have to form an N-well above which only we can able to form a P substrate. So wherever there is a combination of P and N coming, you will be having a reverse diode effect there, reverse biased diode effect. So here one PN, 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 PN. So due to this, at this particular junction, due to this reverse biased diode, you will be having a reverse current ID. That current equation only they have specified here. This is the diode current. So which will negatively impact the circuit. So as the junction temperature increases, this current also increases. So temperature also will negatively affect the junction. Temperature dependence is very important in the case of non-ideal characteristics. So temperature can influence negatively as well as positively. So if you see that junction leakage cases, as temperature increases, the junction leakage will increase. That is the negative impact. But in the case of threshold voltage, as temperature increases, that will make the electron that will give electron high energy. High energetic electron will form at the time of increase in temperature. So electron can move very fastly with high energy. So it will improve the current, first case, by decreasing the threshold voltage. Due to increase in temperature, threshold voltage also decreases. That is the case they have mentioned with this equation. So as the threshold voltage decreases, we need to apply only less amount of input voltage to make the inversion happen. So likewise, the temperature has both the positive as well as negative impact on the uh, non-ideal IV cases. Then comes the geometric dependence. Geometric dependence is the last case that can be the geometry of the circuit can be vary only with respect to the designer. After designing a transistor, we can't able to vary the geometry. Why the geometric dependence is coming to play is actually we have seen the short channel, long channel effect. Both the thing we have explained in that as per the equation itself, I can able to we have seen IV characteristic equation, right? You see here, uh, here W by L is coming in the equation. Beta is mu C naught x W by L. The length of the channel is coming into denominator. But according to the design, we are making it as a constant. We are making beta as constant, right? But while designing itself, if the length of the channel is very, very less means, so it is inversely proportional to current. So if length of the channel is less, current will be high. That is the geometric dependence case. So that's why as the nanometer technology progresses, so initially I explained, right, in IN 4004, we will be having 10 micrometer technology. So 10 micrometer is the length between length of the channel. That is the length between source and drain. Now recently in i7 processor and all using 14 nanometer technology. So 10 micrometer and 14 nanometer. Compare that. So length of the channel is getting reduced as technology progresses, right? So if length of the channel is less, more output current it can be produced. That is the geometric dependency explanation. That's all about non-ideal IV effects.